Okay, just a note, and I mentioned this before, but the following here, 1 over square root of 2L, and I'll leave this proof here as homework. Maybe I'll assign it. It's easy homework. We've done things like this before, at least I've told you how to do things like this before. Right, so these form an orthonormal basis. Uh, for L2 minus L to L. And the proof idea is very simple. Remember, we had a list of 4 different uh, equivalent properties of an orthonormal basis. That you have Parseval's equality, you have the inner product version of Parseval's inequality, and that every element in your Hilbert space can be written as kind of a Fourier series in the sense of L2 convergence, or in the sense of convergence in the Hilbert space. So it's easiest to check Parseval's theorem. So in particular, let's say F is an L2 up here. So so if you have FL, find in the obvious way to LX. All right, so if X goes from I'm sorry, if X goes from minus 1/2 to 1/2, then 2LX goes from minus L to L. All right, so you have FL is in L2 substitution. Now we use yeah, just use Parseval's theorem for L2 and minus 1/2 to 1/2. All right, so in particular, what we have is this general Parseval's theorem, which I'm going to use in a second, in an extremely concrete manner. It's actually really one of the most clever uses of Parseval's theorem I've seen, maybe ever. What we're doing is a pretty famous thing. I think it's by Wiener, Norberto Wiener, famous mathematician, early 1900s. I forget who first carefully studied Brownian motion. I don't think it's Wiener, but uh, anyway, so the general Parseval's theorem is as follows. F is an L2 minus L to L. And let's call this, just like before, let's say this is En. Then minus L to L, X. This is given by the following sum. FEN modulus squared. Alternatively, really the same thing. A lot of people do this. You can write this in terms of Fourier coefficients, where this is going to be 1 over 2L minus L to L. So it's obviously the same thing in that second. Um, uh, it's, or rather, so it's going to be square root of, I'm missing a 2L here. Right. So you square this, you get 1 over 2L squared times this is 2L. And for each EN, you get a 1 over square root. Um, uh, and so you get pull out 1 over 2L. So yeah, you square this, that gives you 1 over 2L, and you pull it out. So yeah, another way of writing this. Red. All right, so yeah, let me talk about Brownian motion. And as stated, if there is interest, I will make a video kind of going through this more rigorously, more, in other words, proving particularly L2 convergence of the sum I'm going to write. L2 in the probability space we're working on. And almost surely convergence requires the Kolmogorov inequality from probability theory. Prove that. All right, so let's say these are IIDs. This is zeta, I think. So independent, identically distributed, and these are distributed. So each one of these is normal, mean 0, standard deviation 1. So what does this mean? So each one of these is a normally distributed random variable, as I said, mean 0, normal, standard deviation 1. These are independent of each other. So that implies independent J. And what's important here is that the expectation, therefore, of this is going to be 0. Because independence says that there's going to be a product of expectations. And these both have mean 0 because we're saying they're mean 0. Right. Right. So they're independent and they're identically distributed from this distribution here. Everything's normal, mean 0, standard deviation 1, and they are independent. And we know might be obvious, but so we know that one is a variance of each one of these. So what is this? By definition, the variance is the expectation of squared minus the square of the expectation, which is 0, of course, because it's mean 0. So that tells me something extremely useful, that the expectation of each one of these squared is 1. That right, so that's good. Okay, so let's say we have t between 0 and pi. So I will admit the intuition here, kind of why this intuitively works, is a bit mysterious. Or rather, I guess, so what I want to prove, I'll prove something about this. Yeah. Right, so let's say we have the following. I wrote this down before. So I claim this is Brownian motion. Okay? And the idea of Brownian motion is very simple. It's kind of like, I always laugh kind of when I say this, but it's probably the best, most simplest description of Brownian motion, where if you're really, really, really drunk and you have equal chance of stumbling to the left or to the right, let's just say it's one dimensional left or right. And yeah, you have equal chance of kind of going to the left or going to the right. That's the idea of Brownian, right? More scientifically, it was first discovered in the early 1800s when you take flower petals and just drop it in water. The petals kind of have, in 2 dimensions, they have equal probability of kind of going in any direction at each time. Right. So that kind of makes sense then, that the expected value at each time is 0 because you have kind of equal chance of going left and right. So they would cancel each other out. Um, but it kind of also makes sense, maybe, that if you square it and then take the expectation, that should be t. I'm not sure. Yeah. Honestly, I'm not too familiar with Brownian motion, kind of in terms of intuition and explaining it. So you could probably Google and find much better explanations. But that's one thing I want to prove. Um, and there's one thing to note: we did not, if these were not present, then you should know how to prove convergence of this. And you would get uniform convergence as long as t is a distance away from pi. And that would be the Dirichlet. Okay. Proving this converges, well, the best you can do is almost surely, because these are random variables. And in fact, what you can prove is the following. Uh, Switch to black. All right, so if Bn of t is the following. So if it's kind of the same thing except stopping at n. Yeah, and this is what is not easy. I mean, it's not hard, but it takes real probability to do. Um, so as n goes to infinity, this converges to b of t almost surely in the sense of the probability that this is true is 1. And you can prove that this is so actually you can prove bn minus b squared equals 0. Okay, so it's kind of, you can use this to carefully show that the expectation of b of t squared is t, but that's a little tricky. So what I'm going to do is kind of the next best thing, it kind of says it should be, is that the limit as n goes to infinity of the expectation of Bn of t is t. And this is, so one of the main properties of um, Brownian motion is that this is true. And almost the same proof will give you the following, and I'll leave this as a homework. Kind of the other property, one of the main kind of properties you need of Brownian motion is that the covariance, which is going to be b of s t, is going to be the minimum of s and t. It's actually going to be almost the same kind of calculation, except you're going to do the inner product version of particles theorem. We're going to do the L2 version of particles theorem. Okay, so yeah, how does this proof work? And it kind of, so what's nice about this proof, it kind of tells you why you want to use this Fourier series if you're going to write Brownian motions, right? Yeah, so the proof is a really, really, really nice, easy calculation. It's a Parseval's theorem. So for t between 0 and pi, let y t of x be the following. One, if absolute value of x is less than t, is less than pi, 0, otherwise. Uh, Redundant here. Yeah, and to be clear, I want this to be a function defined on minus pi to pi. So x is pi. Okay, so yeah, easy sanity check. So here's minus t, t minus pi. Pi here is 1. And so blue. Yeah, so the graph is just this here, and then this here. So one that's absolute value of x is between is less than t, and 0. All right, so let's start computing. Yeah, I'm going to use Parsifal's theorem. It's that simple. So in particular, so yeah, what I'm going to do is use this here. I'm going to use this here with L equals pi, right? Fourier coefficients, yeah, these here FENs are going to be very, very easy to compute. So yeah, L here is going to be pi. So take the L2 norm. I have to do f of t. I guess I could y. Sure, y is keeps doing that. The hell is going on? Okay, so well, there's really nothing to do here, right? Because it's just minus t to t, and then it's 1. So it's just t. On the other hand, so FE0, and remember the ENs. So let me at least these are. Sell some room. I'll erase the ENs in a moment. Black one. Right? Right, so E0 is just 1 over square root of L. So same thing, it's literally just 1 over square root of 2L minus pi of f x. And that is just 2t. Same thing, 2t here, because it's just 1. Out 1 over square root of 2L. Same thing, minus t to t. 1 doesn't matter if it's squared, anything there. So that is 2t over square root of L. And you want to simplify this, just multiply and divide by square root of 2. So it's t square root of 2 over square root of. On the other hand, if n is not equal to 0, it's an easy calculation. So again, it cuts it off to minus t to t. It's just 1 from minus t to t. So we have e to the I X N over L. And we'll get the sine. Never had the erase. It's weird. Um, right, so it's going to be I forgot to mention L. Yeah, sorry, I forgot to mention L is pi. So it's a pi here. And the pi here. And so this is so these go away. I'll put the I up here. I thought it was gonna be. I thought it was looking a little weird. That put the exponential here, and then replace that with the. Okay. And this. Maybe it looks a little neater. INX. Whatever. All right, so this is going to be 1 over square root of 2 I over sorry, so minus because inner product makes this complex conjugate, which is minus. So this is going to be minus IN e to the minus INT minus e to the INT. Well, much easier if we multiply top and bottom by -1. So get rid of this minus. And then that minus will stay. But this will become a minus, and this will become a plus. All right, so the next thing to do is probably easiest thing to do is just multiply and divide by 2. 2 here, 2 here. And lo and behold, this is sine. So to simplify this, you get, again, 2 over square root 2 is root 2 over pi, just sine and t over, and you got the root here. Root 2 over root pi, Peter. Right, root 2 sine and t over n. This here, without the n here, this equals sine n. All right, so what is my conclusion? So actually, let me make this a little neater and move this up here. Let me erase this here. sine n e. It's up here. Okay, so let me get rid of this here. All right, so this equals 2 root 2 over root pi. This for n not equals 0 equals this. And you'll notice that when n is negative, it's the same thing as when n is positive because sine is odd. So when we sum up, we got the 0 term, and it's going to be 2 times the n1 to infinity sum. With n equals -1 to minus infinity gives you the same thing as 1 to infinity. So conclusion is that this integral here from minus pi to pi to t is going to be this sum here. Again, that equals this here plus 2 times this sum here. And this is square this 2t squared over pi. Right. So 2n equals 1 to infinity, 2 over pi sine squared n t over n. And I have absolutely no idea how else you would get this. I don't think you would get this from Fourier series directly. Because it's not a Fourier series. Sine squared, you don't get squared of exponentials from Fourier series. So I have no idea how you would get this without Parsons. But yeah, this is the conclusion. 2t for t between 0 and pi is equal to this. All right, so, and of course, just bring in a 2, it's going to be 4. Four. All right, so you can maybe see what's going on. And in particular, because we're just dealing with a finite sum, there's no issues with interchanging sums and expectations. Right, so in particular, let's do this. I don't know why I have a b of t here. Want b of n to be this. Okay, it's kind of a mess, but so let's at least get Bn of t squared and then take expectations. So I'm just squaring this. Bigger. Yeah, so you square this. Okay, you should see kind of what's going on here. It's very akin to having orthogonality. So it's nu 0 squared t squared I plus 2 nu 0 t over square root pi times the sum here. That's the two cross terms. And then last but not least, it's going to be a double sum. Say n and then m, squaring this last term here. So this becomes 2 over pi sine n t and and m t over m times, right? Yeah, and you can kind of even see if you want to do this, but with Bn of t, Bn of s, well, yeah, you would need that other version of Parseval's theorem. All right, so what am I doing? I am going to take expectations. So if I take expectations everywhere, well, let me do this. This is fine, but let me pop in the new 0. And it's all finite sums, so everything I'm doing is fine. Nothing finite sum. So I'm taking the expectation. And then again here, expectation. All right, well, point is, I guess I'll use blue. This is 1. We already set expectation of normal random variable squared is 1. Oh, sorry, expectation of the normal random variable squared is 1, because it's 1 variance. This n is 1, so this is always going to be 0. And this here, as usual, we already did this. It's 1 n equals m, 0. If n is not equal to m, so I think it's just neater to rewrite things. So the conclusion is the expectation of Bn t squared is going to be this sum here but again, m has to equal n, so I'll just write one term here. So you not want to forget this. So t squared I actually, so one thing I want to do, I've done this before. I'll just divide everything by 2. So that 2 goes away, this 2 goes away, and this becomes the 2. So yeah, we'll see we get exactly this. So we've already got the t squared over pi. That's good. Need plus n equals 1 to n 2 over pi. Did I really forget to square? No, I didn't forget to square the n. Thought I did, because I usually forget to do stupid things like that. But yeah, it's sine squared n t over n squared pi. So that's exactly what we have here. 2 over pi sum 2 over pi sine nt over n squared. So lo and behold, this equal so it's not equal because we're going from n to little n equals 1 to big N. But from Parseval's theorem, this goes to t. And again, you need some serious probability theory, not anything too hard, but to rigorously justify kind of letting n go to infinity inside the expectation, you do need some probability theory. Again, I'd be happy to go over that if anyone is interested. And I do think, I could be wrong, but I think this might be the most elementary approach to Brownian motion. What's kind of nice here also is if you have a Riemannian manifold, you can probably do Brownian motion on that Riemannian manifold in the same way. Do an eigenfunction expansion with respect to the Laplace Beltrami operator, if that means anything. Certainly, you can do in particular. That should be okay. That should be fine. I looked it up. You can definitely do Brownian motion on a Lie group, where you use the Peter-Weyl theorem to do sort of like a compact loop. Compact loop. General Lie groups are much harder. Compact Lie group, you can certainly do this kind of thing. Brownian motion. Peter-Weyl theorem gives you like a Fourier series type expansion. I have no idea what would be possible on a non-compact Lie group, but those are horrifying. Anyway, yeah. Again, the covariance version of this, almost the same thing. I'll leave that for homework, which is right, this one right here. That yeah, sorry. It meant ends here. Right. So this is the whole. As n goes to infinity, Bn of s times Bn of t converges to the minimum of s and just Parseval's theorem. And yeah, again, this approach was done by Norberto Wiener, I think early 1900s. All right, well, I hope you enjoyed that. I really think this is neat, so that's why I did it. Yeah, well, so long, take care, bye-bye. Next up is the Fourier transform.